Do you know how platforms like YouTube, Instagram, or Google manage to track billions of unique views every second? It sounds simple, but at billions of requests per second scale, it becomes an incredibly complex challenge. In today's video, we will explore how tech giants count unique views quickly without burning massive compute resources. I have worked on similar challenges myself, and I'm excited to share what I have learned with you. If you're preparing for tech interviews, especially system design interviews, this video is a must watch. Hi there, welcome to Tech and Career Bytes. I'm a software professional with over 2 decades of experience, including 7 years in leadership roles at a global product based organization. Let's first understand the problem. Counting unique views on platforms like YouTube, Reddit, Instagram, and Google is valuable for analytics platforms, ad targeting, and understanding the actual reach of content. But when these platforms are generating millions or even billions of unique views per second, how can we accurately and efficiently track unique visitors or interactions in real time? Simple solutions like direct database queries quickly hit bottlenecks when trying to handle millions of requests per second. In this video, we will explore several strategies for counting unique views, starting with traditional database queries and progressing to more advanced techniques such as Redis with HyperLogLog and Sharded counters. Along the way, we will explain why each approach works or does not at scale. So, without further ado, let's get started. The simplest and most straightforward way to track unique views is by using a relational database like MySQL or PostgreSQL. For each unique view, you could insert a record into a table and use a count a distinct user ID query to count the number of unique views. This approach is easy to use for small data sets. But as the data grows to millions or billions of rows, it becomes a performance bottleneck. The database starts to slow down and query times increase. Costs skyrocket as scaling the database becomes expensive, both in terms of hardware and operational complexity. So, what's the next step? And what's the solution? Redis, a lightning fast in memory data store that reduces database load by acting as a cache. When a user views the content, the system first checks Redis to see if the user has already been counted. If the user is not found in the cache, the system queries the database and caches the result in Redis for future requests. Redis can be configured with eviction policies to remove old or irrelevant data, optimizing memory usage. Here is a sample code snippet for this approach. Redis speeds up response times and cuts down on database load by operating entirely in memory, making it incredibly fast. But as the views scale into the millions or billions, even Redis starts to feel the heat. Storing millions of unique user keys becomes expensive in terms of memory consumption. Also, to make room for frequently accessed keys, depending on the eviction policy, Redis might remove keys before they expire, leading to inaccuracies in unique view counts. While caching helps mitigate database load, it is still not ideal for handling billions of views or millions of unique users per second. That is where probabilistic data structures like HyperLogLog come in. Let's understand what a HyperLogLog is, how it works, and how it addresses the challenges of counting unique views efficiently. HyperLogLog or HLL is a probabilistic data structure that estimates unique elements in a data set using a fraction of the memory traditional methods require. Unlike storing each individual user ID, HyperLogLog tracks unique views using hashes and bit arrays. This makes it ideal for platforms that need to track unique interactions across millions of users with limited memory. HLL excels in situations where exact accuracy is less critical, but low memory consumption and high speed are priorities. Redis natively supports HyperLogLog with commands like pfadd and pfcount. Let's understand how HyperLogLog works. To begin with, HyperLogLog is initialized as a data structure with a fixed size array of 2 to the power of p elements, where p defines the precision. The higher the value of p, the more accurate the count, but at the cost of using more memory. Each element of the array starts at 0 and tracks the number of leading zeros from the hash of each input. For example, if you allow an error rate of 0.81%, that is less than 1%, the precision value p is determined using the formula shown here. When a unique item, such as a user ID or view, is added to HLL, the item is first hashed into a large binary number using a hash function like SHA-256 or murmur. The hash output is then divided into two parts. The first p bits determine which element in the array to update. The remaining bits are used to count the number of leading zeros, and this count is stored in the selected array element if it exceeds the previous value. Suppose the hash function converts a user ID into binary string shown here. The first four bits 1100 convert to decimal 12, selecting element 12 in the array. The number of leading zeros in the remaining bits is 0. Therefore, element 12 in the array is updated with the value 0, since there are no leading zeros here. If another user ID is hashed to the string shown, the first four bits 1100 again select element 12. The number of leading zeros in the remaining bits is 1. Element 12 is updated to 1 as it is greater than the previous value 0. Later, if another hash maps to element 12 and has more leading zeros than 1, example 3, the array element is updated with the new value 3. HLL does not store actual user IDs, but maintains an approximation of how many unique elements have been encountered. The unique count estimation is based on the distribution of leading zeros across the array. The more leading zeros observed, the higher the likelihood that a large number of unique elements have been seen. To estimate the count, the algorithm computes the harmonic mean of the values in the array using the formula shown here. If we assume that element 12 holds the value 3 after the updates and that all other array elements still have the value 0, since only element 12 has been updated, applying the formula we get E equals to 11.42. Thus, based on the example, HyperLogLog would estimate around 11 unique elements encountered so far. While HLL provides only an approximation, it is highly efficient in terms of memory usage and accurate within a defined error rate. For instance, with a precision of p equal to 14, the error rate is around 0.81%. Here is how you can implement HyperLogLog using Redis in Java. Each time a user views a piece of content, the user's unique identifier, like their IP address, user ID, or session ID, is added to a Redis HyperLogLog structure using the pfadd command. At any point, the pfcount command can be used to estimate the number of unique users who have viewed the content. HLL is fast. It is memory efficient. But here is the trade-off. HLL provides only an approximation. The count might not be perfect, but for platforms tracking millions of views, this approximation is often good enough. For large-scale platforms like YouTube or Instagram, HLL strikes a balance between memory usage, speed, and accuracy, making it a popular choice for tracking unique views. For platforms with massive scale, where even HLL on single node Redis setup might not suffice, sharded counters can help. In sharded counters approach, the total view count is spread across multiple Redis instances or database shards to distribute the load. Here is how HLL with multi-node Redis cluster works. Instead of storing the view count in one Redis key, the count is distributed across multiple shards. To retrieve the total count, the system aggregates the counts from all shards. Sharded counters allow multiple nodes to write to different shards concurrently, improving performance. Here is a sample Java code to implement this approach. This approach allows for horizontal scaling, ensuring your platform can handle even the highest traffic loads. But it does add a layer of complexity, especially when it comes to aggregating results and ensuring data consistency. So, where does that leave us? Ultimately, the best solution depends on your platform's scale and traffic. For small scale applications, a traditional database query might work just fine. As your traffic grows, Redis becomes a powerful tool to reduce the load. And when you hit millions or billions of views, HyperLogLog and sharded counters offer memory efficiency and scalability you need to stay responsive. That's the overview. The next time you're watching a video or interacting with content online, you will have a better understanding of the technology behind the scenes. And remember, when operating at scale, efficiency is key. Let me know what you think in the comments. If you found this video helpful, give us a thumbs up and subscribe to our channel for more interesting tech topics. Do check out our other videos on software performance optimization case studies, coding, system design, big data, and career growth. My name is Rupa, and I thank you so much for watching this video. See you next time.